Hello, everyone. Welcome to this session of SDC 2024. As always, it's a pleasure to come and present in this extremely important Storage Developers Conference, as well as meet with all of you fellow enthusiasts in the field of storage. So today I'm going to talk about the Intel IPU and specifically how the Intel IPU accelerates NVMe Initiator logic and how that work sits on top of the SPDK framework. My name is Debashish Chatterjee or Deb Chatterjee. I am a Senior Director of Engineering within Intel, and my team distributed worldwide develops about 90% of the software that is part of the IPU SDK. Our primary customer is Google, but this technology is available for any broad market consumption. I came and presented IPU in SDC before, so this may seem a bit of a repeat, but it's a new class of device in the data center. It accelerates different aspects of networking, the LAN processing, NVMe, RDMA. In addition, it includes purpose-built accelerator blocks for compression and encryption. This Intel IPU, codenamed ES2100, is commercially available. So we are all familiar with the concept of SmartNIC, which is network computation intensive work that traditionally happened on the CPU to offload it on an acceleration device. There are multiple ways in which IPU is different from just a SmartNIC. First of all, it provides that proper isolation of customer workloads from infrastructure tasks. That isolation is carefully built in the different aspects of the hardware and software. It does not just offload data plane, it offloads the control plane also. As you can see in the diagram, there are 16 data center class ARM N1, Neoverse N1 cores available, and that's what the customers can use for control plane offload. Overall, the system is very highly programmable, and it provides excellent support for storage use cases, both RDMA and NVMe. But today, I am specifically going to talk about NVMe Initiator offload. This is kind of a data sheet for the IPU. It's a bit of an eye chart, but it's a 200 gig device capable of up to 200 million packets per second. It has PCIe Gen 4 16 lane, high performance compute through the Neoverse N1 cores. There is next generation IO virtualization support integrated in the form of SRIOV as well as SIOV. We have this concept of adaptive virtual function, which are PCIe virtual function as well as physical functions also that are compatible across multiple generations of these IPU devices. So once you migrate from one generation to the next generation, you do not have to necessarily change your driver immediately. All the existing features will be supported with the prior driver. IPU is also unique in two aspects from a SmartNIC, that it can become the center of the platform architecture. You can construct a platform where IPU is the first one that gets out of reset, and then it takes other acceleration components such as GPUs, NPUs, and even CPUs out of reset. in that platform model, the CPU is just another accelerator focusing mostly on running complex applications, AI/ML applications, HPC applications, other kinds of applications. But it's really the IPU that is the center of the universe. And also another aspect in which the IPU brings in a change in the platform architecture is you can also build an IPU-centric security architecture that can also be distributed. You can build this security architecture spanning across multiple IPUs. And for those kind of security operations, it has support of many different types of crypto operations. Once again, this is commercially available right now. This is the picture of an adapter, the one that we call MACA peak, with the IPU shown on it. It has all these different hardware offloads that I just mentioned. Let's talk a little bit more about IPU's role in storage workload, particularly with the NVMe processing engine. In this picture of the IPU, there are two things that are highlighted as blue rectangle because these two things work together to create this NVMe Initiator acceleration. One is an NVMe Initiator hardware block itself. It works along with this look-aside crypto and encryption, crypto and compression engine, or LCE, to provide it some unique capabilities. And I'm going to talk about some of these capabilities. One such unique capability is being able to chain operations such as compression followed by crypto, crypto followed by a direct DMA, encryption followed by a direct DMA. There are many types of operations that you can issue a single command and those can be chained. And that provides a very significant performance advantage. So for LCE, when the data is at rest, it provides device level encryption, storage level encryption, data protection on disk, and also this chained operations such as compression followed by encryption. Let's look at how IPU changes the picture of the NVMe Initiator from a standard NIC to an IPU. You're all familiar with NVMe over Fabric. NVMe over Fabric is a protocol through which the hosts connect to remote storages across networking fabric. In a standard NIC, host CPU cycles are consumed by the operations in the NVMe over Fabric software stack. And NVMe over Fabric software stack is either in Linux kernel or it's in the user space running on the host. One of the most important things that the IPU does is it frees the host CPU for customer workload. It frees up the host CPU. And this is particularly important for the cloud service providers because they want to be able to rent out as much of the available compute to their tenants and monetize those code instances. So this is one direct benefit for cloud service providers. And what happens is IPU kind of becomes man in the middle. The host treats the IPU as NVMe controller connected over PCI, and then eventually NVMe over Fabric is performed on the IPU. Let me give you a little bit more detail on that. Essentially, what the IPU does is it provides a number of NVMe PFs and VFs to the storage application. The storage application connects to these NVMe PFs and VFs and sends storage commands. These storage commands are captured by a hardware block inside NVMe. These commands include command descriptors for fetching remote target, etc. These commands are then sent to the ARM cores. And the ARM cores initiate NVMe over fabric or NVMe over TCP with the remote storage. And so the data then gets seamlessly transferred back to the host. One of the software library that we leverage very heavily for our work is SPDK, Storage Platform Development Kit. It's the modular design of SPDK that enables us to provide a clean integration with the IPUs NVMe Initiator. The NPI or NVMe Protocol Initiator transport interfaces with the NVMe layer. NPI transport interacts with IPU SDK, which is what we build and provide, and also the associated APIs for device configurations and commands processing. QAT or Quick Acceleration Technology has been offered by Intel for a number of years. QAT provides acceleration for different kind of encryption operation as well as compression operation. Within IPU, what we have is the latest generation of QAT, and in the IPU for the first time, we are bringing one unique feature that has never been implemented before on any of the prior generations of QAT, and that operation is the service chain. IPU has support for two new compression formats that was never accelerated in hardware before. These are Z standard and Snappy, and it also has support for some new compression encryption formats as well. But one of the unique capabilities of QAT that is part of the IPU is being able to do service chain. So our NPI transport interacts with the Quart SDK, and it is responsible for the data movement between the host and the IPU memory. I'm going to talk a little bit about the SPDK Acceleration Framework. So again, pretty much everyone here is familiar with SPDK. It supports protocols such as NVMe over TCP or NVMe over RDMA or NVMe over fiber channel, supports iSCSI. It supports a number of virtualization protocols such as Vertio SCSI, vHost, Vertio Block, etc. It provides a number of services. One such service is logical volume, combining multiple physical volumes into one logical volume and presenting that abstraction. GPT is the new evolved form of partition table, the GUID-based partition table, and it also supports other kind of caching and pooling mechanisms. In terms of providers, all of these protocols such as NVMe, Vertio, Ceph, RVD, etc., these are all supported. It is open source and BSD licensed. It is optimized for leading edge storage solution and an ideal framework used for IPU, DPU based storage solution. Some of the evolutions that DPDK brought in the packet processing side, though built completely differently, SPDK has similarly brought similar kind of innovations in the storage side. SPDK already has an acceleration framework, and you can go to this link and read more about it. This acceleration protocol, what it does is whatever are the compute heavy offloads for storage, it offloads those to the hardware accelerator. And in this category are things like encrypt, decrypt, compression, decompression, CRC calculation, and other things. There are hardware accelerators already available. Along with IPU, there are other kinds of hardware accelerators available that can take the advantage of this Accel framework. One is called IOAT, or Intel IO Acceleration Engine. There is also Intel Data Streaming Accelerator Engine, or DSA. For fallback path, in case there is some kind of exception or somehow the hardware capacity is saturated, there are other fallback software plugin module available. For instance, ISAL, which is Intelligent Storage Accelerator Library, that is used for optimized CRC32 calculation. When we did this work for the IPU, and when we looked at how we are going to integrate with SPDK, we felt that there is a motivation for change. What were those motivations? The current approach, what it does, it's a single operation is requested or performed on an IO buffer. And if there are many stages of IO buffer processing that leads to many operations on accelerator, it is not just time consuming, but also the overhead of coordinating all of these, collecting the data, and then etc. So some of the new requirements that we wanted to bring to this framework is, for instance, integrate with the new capabilities in hardware accelerators such as IPU, being able to chain operations on IO buffers, and to be able to schedule operations that are residing in different layers of software, and also wherever we can do some of these new changes can be offloaded to the IPU LCE engine. So we requested these changes and got many of them already done and integrated with the SPDK framework. We introduced chained operation in Accel framework API. We adapted some of the SPDK components to new hardware capabilities through the use of new APIs. And we validated this approach with the IPU LCE capabilities. So whatever I am talking about, it is not just proof of concept or even early prototyping. This is in production with Google and available for consumption with any new customer. This provides improved performance and reduced pressure on the memory bandwidth. So these are some of the new APIs and usages that you can find in the documentation also. So there are these SPDK Accel driver ops, and within that we introduced APIs such as execute sequence and get operation info, SPDK Accel sequence continue. There are user APIs allowing users to schedule operation and build operation chains such as append crypto, append encrypt, append copy, etc. So this influences a number of components and component layers: the BDEV layer, the NVMe over fabric layer, the NVMe over TCP transport layer, etc. One of the core areas where we think we have been able to make an impact is in the optimized IO buffers. So some of the key innovations that we made are in terms of being able to do deferred buffer allocation. which is important for I/O reads and less vital for writes. We introduced the concept of something like a fake buffer, which is some kind of a placeholder buffer until the actual buffers are allocated later. Our innovations also results in faster buffer freeing, which is very important for I/O writes. They are freed after submitting to network. So with this deferred allocation and faster free, we believe that we are able to get the system in a situation where there is less pressure on memory size and the amount of memory that is needed. And all of these are actually implemented in open source SPDK core instead of in vendor specific internal code. The vendor specific code is responsible only for programming the vendor hardware. Again, pictorially showing in the previous approach, you had doing DMA plus crypto and doing CRC as two separate operations with two buffer translations. This particular DMA plus crypto is often performed outside of the SPDK framework to reduce memory bandwidth cost. But overall, it results in an overall ineffective buffer management. With the new approach, all buffer transformation requests are a single operation, single transformation, and managing this transformation perfectly fits into the SPDK framework. It does not incur any additional performance penalty. And I already talked about the benefits of this delayed buffer allocation and early freeing of buffer. It's kind of showing the two approaches side by side, the previous approach of two operations and the new approach of combining both operations in one. So in terms of status, SPDK version 24.05 has already been released. This one has the API changes that I mentioned all delivered. The SPDK components, the modified SPDK components are there. And it has all been demonstrated with the IPU that our results show that this new approach makes sense and provides a lot of benefits. What is still to come in future releases is more performance tuning in SPDK layers. So that's what I wanted to talk about today in terms of key takeaways. I think I have been able to explain how the SPDK Acceleration Framework is structured and how it is used. And you have also learned about the hardware capabilities of IPU-like devices and how it can be integrated into the SPDK Acceleration Framework. So this is how we do the NVMe Initiator offload. If any of you want to discuss more of this, you can contact me. I'm deb.chatterjee@intel.com. And thanks for listening to me.